And this is a joint work with Domenico Lembo, Riccardo Rosati, and Domenico Fabio Savo. And this paper has been accepted at IGCAI 2020, and this is an extended abstract presented at Description Logic workshop. Controlled query evaluation is a confidentiality preserving framework in which a policy specifies that certain data have not to be disclosed, and then a censor alters query answering in order to guarantee that such data are not disclosed. Controlled query evaluation has been studied over databases and only recently over description logics. Here we study over description logics, and for us, a CQE instance is a triple where there is a T-box and A-box, so a classical knowledge base description logics. And then we also have a policy. A policy here is a set of denial assertions where each denial assertion is of the form for all x, conjunction of atoms implies bottom. And the assumption that we make is that the T-box union the A-box and the T-box union the policy are both consistent first-order logic theories. We study the notion of censor under the indistinguishability-based notion. And the intuitive idea is that for each A-box and query, a censor returns the same answer as it would return on another A-box that does not violate the policy. So in this way, when a user poses a query over the ontology, the privacy is guaranteed by the fact that the user cannot understand which of the two A-boxes she is querying. Before formally defining when a function is an IB censor, we use the notion of CL-CQT, which is a function that takes an A-box and returns all the Boolean conjunctive queries that are entailed by the first order theory T union A. We can now define when a function is an IB censor. So we say that a function chance is an IB censor for a T-box and a policy if it satisfies two conditions. The first condition is that the theory of the censor for the A-box is a subset of all the Boolean conjunctive queries that are entailed by the T-box union the A-box. And the other condition is that there is another A-box A prime, and the two theories under the function chance are the same. And this A-box A prime is a consistent with respect to the T-box and the policy. Clearly, we want to study the notion of IB censor. We want to study the optimal IB censors. And intuitively, an IB censor is optimal if there is no other IB censor chance prime that can do better. Where do better is the notion that the theory has more things with respect to the function chance. And we denote by opt IB chance all the optimal IB censors for a T-box and a policy. Here we have an example. The T-box says that every VIP customer is a customer, and the policy does not want to disclose the customer that are also suppliers. Here there are three censors, where the first one, when there is an individual that is both a customer and a supplier, it removes the assertions customer and VIP customer. The other one removes the assertion supplier, and there is a third one that removes the assertions customer and VIP customer and also supplier. Clearly, one can verify that chance 1 and chance 2 are both optimal IB censors for TNP, whereas chance 3 is not. In literature, it has been studied a different notion of censor, which is called confidentiality preserving censor. And the idea of this censor is to return a theory that contains all the facts that are entailed by the T box and the A box, but it does not violate the policy. As a first contribution in this work, we have provided a detailed relationship between the notions of IB censor and the notion of confidentiality preserving censors. In particular, for a specific case of CP censors, we have a result that says that reasoning on all optimal CP censors is the same as reasoning on all optimal IB censors. And this is the first contribution of the paper. Then we have moved to give an optimal IB censor, to construct an optimal IB censor, and we have devised the OptChance algorithm. The OptChance algorithm takes in input a DLiTR T box, a policy, and an A box, and it returns a set of facts, another A box. The steps of the algorithm are as follows. We first create the closure of all the facts that are entailed by the T box in the A box. Then we pick each of these facts and we try to add it in the A box A prime. And we do this only if the fact alpha does not violate the policy. So each time we pick a fact in AT and we add it to the A prime only if it does not create inconsistency. Clearly, this algorithm is a polynomial time in the size of the A box, and we have that the first order theory T union the result of this algorithm always corresponds to the theory of some optimal IB censor for the A box A. However, there is a problem, and the problem is that when we randomly choose some optimal censor, we have to do some decision. We can prefer a fact with respect to another, and this obviously may result in discretionary results. In order to overcome this situation, we first have looked into a sort of skeptical entailment. And in skeptical entailment, we have that a query has a positive answer if it is entailed by each optimal censor. However, skeptical entailment is intractable, and indeed one of the results is that checking whether a query is entailed in all the optimal, in the theory of all the optimal censor is a co-NP complete problem in data complexity, so in the size of the A box. So we have investigated a different notion, and it is the notion of quasi-optimal IB censor. The idea is that a quasi-optimal IB censor is as close as possible to the theory of all the optimal IB censors. And it is defined in the following way. We say that a function chance is a QIB censor if it is an IB censor, if the theory is a subset of the theory of each optimal IB censor for each A box, and if there is no other IB censor, chance prime, which satisfies condition 2 and it behaves better of the function chance. And as a theorem, we have that this QIB censor always exists and it is unique. We can now look at an example. As before, we have the T box states that every VIP customer is a customer, and the policy does not want to disclose customers that are also suppliers. Here, the QIB censor is the one that when there is an individual that violates the policy, it removes the assertions customer, VIP customer, and supplier. And so we want to study the decision problem called the QIB entailment that takes a T box, a policy, an A box, and a query, and it checks whether the theory of the censor, of the QIB censor for A entails the query, the conjunctive query Q. And we have shown that QIB entailment is in H0 data complexity, and in particular, this problem enjoys first-order logic reproducibility. We cannot enter into details of the algorithm, but we can look at the main idea. So as before, we have the T-box and a policy, and then now the query is give me all the customers. The algorithm applies the following 4 steps. First of all, the policy is rewritten with respect to the T-box. Then the query is rewritten with respect to the T-box. And then there is the third step, which takes each query in the set Qt, and for each concept occurring in the body of the query, and analogously it does for each role, it checks whether such concept unifies with the body of some denial. And if it is the case, if this is the case, then to the body of the query, we add the negation of the denial. After these third step, it applies a 4th step, which rewrites each concept and each role with respect to the T-box. We can look at the example customer. Then customer produces customer and VIP customer. We pick the first query, and customer unifies with the first policy. So the first query produced is customer and not supplier. Then we pick the second query in the set, VIP customer, which unifies with the second denial in PT. And then we also get VIP customer and not supplier. So at the end, the rewritten query is give me all the customers that are not supplier, and take the union with all the VIP customers that are not supplier. And so we have the theorem that says when we have a T-box, a policy, and a conjunctive query, when we rewrite this query using the algorithm QIB perfect ref, we have that for each A-box A, the theory of the QIB censor for A entails the query if and only if the A-box entails the rewritten query. So this is a first-order logic reproducibility result. We have reduced the problem of QIB entailment into an evaluation of the query over the A-box. And so QIB entailment is in AC0 in data complexity. What we want to do as a future work, we want to formalize richer data protection scenarios and going beyond only the deductive abilities of a possible malicious user. And also, we want to investigate expressive forms of policy in the enforcement of confidentiality. Thank you, everyone, for the attention.